Hello everyone, my name is Elisa Martí and I would like to show you our last work, the colors of ocean plastics. We can imagine a plastic object floating on the surface. Exposition to sunlight provokes photodegradation, so plastics will not disappear, but they will be fragmented in smaller pieces. But also, solar radiation involves the photooxidation process that causes changes in plastic color in two ways, decoloration, whitening, and yellowing, tanning. In the first process, plastic surface loses its original color, changing to lighter color and then to white. Due to oxidation, there is also an accumulation of products in the plastic matrix. It gives yellow or amber color, leading to yellowing and tanning. We were interested in explore the aging plastic using plastic color, but also we thought in two extra variables. The abundance of plastic items increases toward smaller sizes. It happens across time, so we can look for a relation between plastic size and the plastic age. On the other hand, the transport of plastic fragments to distant accumulation is proposed to be a time-dependent process, with the fragments far from shore being older than nearby ones. So, in order to explore aging plastic, we studied the relationships among plastic color, plastic size, and distance to land where samples were taken, because all of them could be in some way related to exposure time in the environment. The study of plastic color is very common. Sometimes people use a simple classification because sorting with few colors, and sometimes they divide in many different colors. In addition, this assessment is highly subjective, and the lack of standardized methods gives difficulties to compare studies and achieve conclusions. So our main goal was define a consistent methodological tool to characterize color in marine plastic samples in order to explore the information behind the plastic color. We collected samples from Atlantic, Pacific, and Indian Ocean during Malaspina expedition. In the years that followed, we included samples from Arctic Ocean, Mediterranean Sea, Red Sea, and Bay of Biscay. We collected samples always in surface waters using a Neuston net. Plastic and organic material were separated in the lab. At the end, we had more than 8,000 plastic items. We divide in shapes, microbeads, pellets, rigid fragments, foam, film, and fishing line. Also, we did measurements of length and area, using a photography and a software of image analysis. We usually use ImageJ, which is a free and powerful software. In order to know the plastic type, a subsample was analyzed using FTIR. Then, we classified by color. We assembled a reference palette with 13 main colors: yellow, brown, orange, red, pink, magenta, violet, blue, sky, cyan, turquoise, green, and gray. And 9 hues from black to white, beside the transparent or translucent, accounted for a total of 120 possible colors. The printed color palette was placed under the Petri dish, and color codes were assigned to the plastic items by visual similarity. To ensure the replicability of the printed version, we had the Pantone codes that are provided in the paper. We also explored a digital semi-automatic method. Getting digital color is possible through a combination of red, green, and blue colors. The RGB include values from 0 to 255. It means that RGB comprises more than 16 million of possible colors. In order to convert all these possibilities in 120 colors, we translate the palette to a simplified RGB color space. Thus, each little ball represents one color of the 120 from the palette. So, to proceed with digital methods, we delimit the border of plastic items using the photo. This area contains many pixels with different RGB score. So firstly, we average the RGB from all these pixels. And then we used the dropper tool in order to get RGB as a coordinate. Finally, we identified the minimum distance between this RGB and the color codes from the palette by proximity in the color space. I would like to divide the results in 3 parts: the result of studying plastic shape with plastic color, the abundance of plastics for each color, and the plastic color in relation to size and distance to land. The analysis of color pattern for plastic shapes showed that film-type plastics were mainly related to the transparent items, while fishing lines were highly related to blue, turquoise, and green colors. For abundant plastic bicolors, our analysis focused on rigid fragments because they are by far the most abundant in the samples. Here we can see the palette as the base of the diagram. The bar height represents the proportion of each color, excluding white, black, and transparent items. If we sum each row for the different main colors, we can see a high proportion of amber colors. It means yellow, brown, and orange, likely related to the yellowing and tanning process. This proportion was followed by bluish color, gray, and reddish color. Projecting data on the hue axis, we found an increasing trend in abundance toward the lightest color that we related to the coloration process. Here, I'll show the last part of results. We were looking for a possible trend in the color spectra, taking into account plastic size and the distance to land. First, we studied the covariance of color in relation to distance to land, and we got 4 main groups explain the color variability. Here we have the results. X-axis represents distance to land, and the y-axis represents abundance of color. I would like to highlight the first principal component that grouped white plastic and light cyan plastic. The abundance of these colors increases offshore, reaching 70% of all items at distance larger than 2,000 kilometers. It suggests that, on the one hand, white plastic could be aged plastic that initially were of another color. It lost their color and over time they became white. On the other hand, light cyan could be also aged plastic, coming from the coloration of dark blue plastic. In fact, blue color can be regarded as an environmental oceanic color. Blue pigmentation is commonly used for the organism living on the surface, being sometimes useful for camouflage. Based on our result, we suggest that blue plastic could be unnoticed by visual predators. However, researchers find blue plastic inside organisms, so we cannot discard another reason. Now we are going to see the covariance of colors in relation to plastic size. Again, 4 main principal components explain the color variability. Here, x-axis represents plastic size and y-axis represents abundance of color. I want to highlight 2 ideas. The first principal component was white plastic, that increases toward smaller sizes. In our results, white plastic was the more abundant color, and it emphasizes that white plastic is aged plastic, plastic with a decoloration across time. But also we found a coupling between light yellow and light brown items. We can see a peak at 10 mm in the abundance of light yellow plastics and a peak at 1 mm in light brown items. In fact, weathering tested with plastic material suggests a typical progressive shift from white to yellow to brownish color upon an extended solar exposure, matching with our finding. So, to conclude, I would like to highlight 3 ideas. In this work, we propose a method to analyze color by using a reference palette. 120 possible colors is not very demanding, but it could be converted to a simplified palette with the aggregation of dark, medium, and light hues. Regarding to the processes controlling the color distribution, photodegradation was related to the loss of color or whitening, while the photooxidation seemed to be related to yellowing and tanning. The preferential intake of certain colors by visual predator could also have some effect on the color abundance of the floating plastic. Thank you very much for your attention, and feel free to ask me any question or contact me to ask.